My name is Anthony Senft, and this is Physics Lab 5, Choose Your Own Adventure. In this lab, I chose to analyze a slinky that's being dropped from rest, but it's also stretched, so there's kind of two components to the slinky. You have the top and the bottom of the slinky, and we're going to determine some of the forces that act on that slinky and why those forces make it fall in kind of an unexpected way when it's dropped. Then I'm going to compare my observed data to a computational model to see if I can get a better understanding of those forces that are at action, that are in play. So some important laws and concepts is obviously going to be Newton's second law. So the primary thing that we use with Newton's second law is going to be net force and the velocity update formula, which is pretty important to the lab. A quick overview of the forces at play here. We have the gravitational force, the drag force of the slinky when it falls, and the tension force or slinky force that we get from the slinky being stretched. So gravity is calculated just like we always calculate it, and that's going to be the mass times the gravitational constant times the directional vector, which is -1 in the y direction in reality, but because I use it in other places in the code, I make it 1 and then negate the gravity. So the drag force is going to be the magnitude of the speed squared times the directional vector times the drag coefficient, which I'll talk about in a moment. And then the slinky or tension force is kind of like a normal force in this situation, so it's just the opposite of gravity. And you'll see why in a moment. So here are observations. We start with the slinky stretched, as you can see here, and I'm mapping the bottom of the slinky in blue, and then we end with them at the bottom. So this doesn't show you too much visually of how it falls, but my video software wasn't working. So I'll talk about what happens in the next slide. So basically, the top of the slinky falls for 5.36 seconds, while the bottom of the slinky stays in the same position, in that origin position. That's because gravity and tension are working on the bottom, while gravity alone is working on the top. So the next point is that the top reaches the origin and it impacts with the bottom. This causes both the bottom and the top of the slinky to fall together, and that's because gravity and drag force are acting on the entire slinky. And then it hits the ground at 8.3 seconds. So here's an overview of my code, the computational model I used. And I said that the ball was 0.25 kilograms. I set the initial position and velocity to be 0 because we're at rest, and the bottom is at the origin. And then I said that the J hat was at 0, 1, 0, like I mentioned before. Then we have the drag force constant, which I said was 33 because of the slow motion kind of altered what was going on. So next we have the first while loop, which is it's from the beginning until the top of the slinky hits the bottom, so that 5.3 seconds. I calculate gravity, calculate tension, like I mentioned earlier. Then I use the velocity and position update formulas to get the new position and velocity. Next, I take my second while loop up until the entire slinky hits the ground. I calculate the effect of gravity and the effect of drag. As you can see, that -b is our coefficient that I mentioned earlier, and then here's the equation that I had on that second slide. Again, velocity and position update formula coming from Newton's second law. So here are the results. In blue, you have the observed data, which is a little all over the place at times, and that's just misclicks, imprecision due to human error. And then you have the position model. It's also a little jagged, and that's likely due to some errors that I'll talk about in a moment, but they are, for all intents and purposes, very, very close together. I think that this is maybe 0.05 meters off at the end of the day. So some room for error. This was a slow motion video, so it necessitated some assumptions. And then some other forces that were acting on the slinky could have been rotational energy or a strong wind. And then the largest reason for a possible discrepancy was the distance that was fallen was uncertain. There was no point of reference in the video that I knew for sure was 1 meter. So in conclusion, the slinky falls in an unexpected fashion. It doesn't just all fall at once. There were 3 primary forces working on the slinky: gravity, tension, and drag. And we see Newton's second law at play. You have the net force that is made up of those three forces I just mentioned. We use the velocity and position update formula to construct this model, and obviously that those formulas are at play in the real world. They're just not actually computed. And then the main question of this lab, can we make a computational model that maps this observed data? And the answer is yes. I was able to do that. You can see it on this slide. It's pretty close. And that's all I have. I hope you learned something about net forces and how they can make things happen unexpectedly. Thank you.